Hi class, this is Dr. Nerz-Stormes. This week's lecture is going to be sort of an amalgam between the Diels Alder Lecture that I videotaped last week and a lecture about solubility or a lecture about recrystallization. I really recommend that you watch both of these. Unfortunately, the Diels Alder Lecture was not delivered last week because of the hurricane, although it is up on Integrity and up on Moodle. And then this lecture, which I'm doing at home, which is going to be on recrystallization, is going to be up on Moodle tonight. Okay? So I really recommend that you watch both of these because whatever I do in lab lecture this week, it's going to be sort of an amalgam because I don't have enough time to do both things. All right, so I want to talk a little bit about recrystallization because you're going to see that we're going to isolate our products from the Diels Alder as solids. Okay, the Diels Alder products are crystalline solids. One of the most common ways to purify a product from a reaction is that is a solid is to use recrystallization. Okay, recrystallization is probably the most common and the simplest way to purify solids. Now you might wonder, why is the product of a reaction that's a solid contaminated? Well, when you do a reaction, very often you get side products, and sometimes the reaction doesn't go to completion, so the product will be cross-contaminated with starting materials. And in this case, maleic anhydride is solid, and some of the other products that can form from the reaction are also solids. Okay, so if the product is contaminated and it's a solid, probably the first thing you think of is to recrystallize it. And recrystallization is based on the idea of differential solubility. This is the idea that the desired compound, the Diels Alder product, will have a different solubility in some solvent or solvents than the side products or than the starting material. Okay? And the basic idea is based on two concepts. It's based on concentration and temperature. What you do is you pick a solvent that's a little bit mismatched with regard to solubility with your compound. And you take the compound and you dissolve it into the hot solvent. In other words, you put the minimum amount of the compound into the hot solvent. And what you're hoping is that the contaminants are either completely insoluble in the hot solvent, in which case you can filter them out at high temperature, or that the contaminants are more soluble in that solvent at low temperature, in which case your desired compound will come crashing out, leaving the contaminants in solution. But all in all, the contaminants are removed by filtration, and it's a very simple process. Okay? There's a lot to picking that solvent, and I'm going to talk about that in a minute. But before we get into the process and write how it occurs, I want you just to think a little bit about what you already know about solubility. So if you just go in your kitchen, one thing you know is that solubility depends on temperature. So you could go in your kitchen today and do this experiment. Take a glass of ice water, okay, and then take a glass of hot water. Have them be exactly the same volume, like say both 8 ounces. And you can take some sugar and you can start shoveling that sugar into the ice water slowly and stirring it. Shovel that sugar into the hot water slowly and stir it. And you will very quickly determine that hot water will hold much more sugar than cold water will. So solubility is directly related to temperature. So in other words, with our crude Diels Alder product, we're going to be able to get more of it into a hot solvent than a cool solvent. Okay, so you already know this, and if you think about kind of your common sense knowledge, this experiment, this recrystallization will make a lot of sense to you. Okay, you also know solubility is based on the polarity of the compounds, right? So you already know there are probably some compounds that would not dissolve in your water at all, and then there are other compounds that would be more soluble in water, such as, say, sodium chloride, something like that. So it's structure dependent. Solubility is structure dependent. And then the other thing you know is that solubility is based on concentration. So you could do an experiment where you had a big pitcher of cold water and you had a glass of cold water, and which would you discover could hold or could dissolve more sugar? Well, you would discover the larger volume could dissolve more sugar. Okay? Now, recrystallization is all about what I call exceeding the solubility limit of the solvent. Okay? Or exceeding the solubility limit, which means you get the compound to come out, or exceeding the solubility by raising the temperature up. In other words, loading more molecules in because you've raised the kinetic energy of the solution. Okay? So let's just talk a little bit about the general process. So let's say I have a crude solid. I have some crude solid. I might not even know what contaminants are in there. I might just have guesses based on the reaction that I've done. What would I do? I would dissolve the compound in the minimum amount of a hot, appropriate, and I'm going to say appropriate here, and you'll see what I mean by that, solvent. Now this picking of the solvent is kind of a little bit of guesswork, and very often you have to do a little bit of playing around and experimenting to figure out what the solvent is. And as you'll discover in our lab, sometimes one solvent is inadequate and you have to use combinations of solvents. So what do I mean by an appropriate solvent? An appropriate solvent, if ideally chosen, would be a little bit mismatched with regard to the solid. In other words, the compound, the desired compound, would be soluble in the hot solvent and relatively, notice I say relatively, it's not going to be completely insoluble, relatively insoluble in the cool solvent or the room temperature solvent, okay? That would be one point, okay? You'd want this solvent to be relatively inert. I hope that makes sense. You don't want it to react with your compound. You'd want it to be relatively volatile because you'd want it to evaporate off the crystals. You'd want the crystals to dry. You'd also want the contaminants to either be completely insoluble in the hot solvent or more soluble in the cool solvent. Okay? This is kind of like the parameters for it, all right? So what you're doing is you're manipulating these solids, and you're hoping they have different solubilities at different points in the process so you can get rid of them. All of this will allow for a separation. So what you do is you take your crude solvent and dissolve it in the minimum amount of hot appropriate solvent. What does that mean? That means that whatever you're using, you've kind of picked something that you think has a slightly mismatched dipole moment with your compound, or you've actually experimented by taking a little bit of compound and testing it in a solvent, in a hot solvent. And you've ascertained that the compound goes in when it's hot and some of it comes out when it's cold, or most of it comes out when it's cold. You've experimented. So you've worked this out, and you have a solvent you think is going to work. And what you're doing is you're adding the solvent to your crude solid in increments, you know, boiling it and keeping it really hot, but adding it in increments until all that crude solid appears to go in, or it appears to not be changing anymore. Perhaps there's some ionic material in there that never goes into solution, but you would get to a point where you would stop adding it because you would feel like it was all in solution. Minimum hot, and I should say almost boiling. We're talking almost boiling here. Okay? So then what do? Check for insoluble material. Okay? If you have insoluble material, what I mean by this is you're adding solvent in increments. You're looking at your solution. You get to a point where you've got your solution, and by the way, we're using an Erlenmeyer for this, okay? You've got a boiling stone in there. Okay, you're adding solvent, and you get to a point where you notice there is particulate matter that just won't go into solution. You've added another milliliter, it's not changing. Another milliliter, you're boiling it, it's not changing. If you get to that point, that means you have insoluble material or insoluble contaminants. What would you do at this juncture if this were the case? Well, this gives you the opportunity to separate some of the contaminants. What you would do here is a hot gravity filtration. Okay, hot gravity filtration. All right, what is a hot gravity filtration? Okay, so this is a flow chart of sorts here with a lot of information on it. Okay, hot gravity filtration what you do is you use kind of a special setup. You take an Erlenmeyer, a small Erlenmeyer, you put a little bit of the solvent in, like say 2 ml of the hot solvent, over the top of your Erlenmeyer. You put this on a hot plate, and you're warming that solvent. You're actually creating what I would call, like, it's not steam, but let's say we're using ethyl acetate. You would be creating like sort of like vapor in there, so it's sort of refluxing. And then on top of this apparatus, you would put a clear glass funnel with a piece of fluted filter paper. So if you ever have to do this, we'll show you how to flute filter paper, or if you need to do that this week. And then what you would do is you take your solution that you had prepared that has this insoluble material in it, hot, while it's hot, and you would filter it through this fluted filter paper. You want it to go through very, very quickly, and the vapor from this solution would be rising up and hitting this glass funnel. And you'd filter this through very, very quickly. Now you might think, why do you have to filter it through quickly? Why do you need this fluting? A fluted piece of filter paper is sort of like a coffee filter. You know how a coffee filter is? And it's got those those folds in it. You want to have a huge surface area because you want this to go through very, very, very rapidly. And you want it to go through very rapidly because you're worried about your desired compound coming out of solution, because it's sitting in the hot solution, right? If you take your cup of hot tea that's filled with sugar and you bring it down to ice temperature, you would see sugar crystallizing out, because the desired compound is going to be in solution here. The undesired compound, you're filtering it out. It has to go fast, because if it goes slowly, if it percolates through slowly, the crystals are going to form up here. We want the crystals to form down here. So again, the design here is to create some vapor that's going up on this funnel, warming it, and then having a large surface area so the filtration is really fast. Okay? In this situation, the residue would be the insoluble contaminant. Okay? The filtrate, which we could also call the mother liquor, okay, is going to have in it your desired molecules, but possibly also some undesired molecules that we hope will stay in solution. So then what you do is you slowly cool. So this will be in here. Everything ends up in here. This should look like a clear solution. I know that's a horrible picture. Okay? This should be a clear solution. So you slowly cool to room temperature. It's usually not advisable to use ice, because ice might get it down so cold that any contaminants that are in the solution will come out of solution, and we don't want that to happen. So slowly cool it to room temperature. And then what you want to do is vacuum filter after complete crystallization. Okay, so what do I mean by that? Well, you guys have vacuum filtered before, so I'm assuming you know how to set up a vacuum filtration apparatus, okay? But when you vacuum filter, and remember, you use vacuum filtration when you are trying to isolate a desired solid and you want it to get really dry, okay? If your desired compound is in the filtrate, you do not use vacuum filtration. We've discussed this before, but it's important. So you do the vacuum filtration. In this case, the residue is presumably the desired product. Okay? In this case, the filtrate, which I could also call the mother liquor, because it gave birth to the crystals. Okay? The filtrate presumably has some desired compound and maybe some contaminant that is soluble in the mother liquor. Okay? So this filtrate, and I'll draw a diagram of this in a second. The thing you have to realize is when these crystals grow, like if you have a flask, and you have allowed this flask, you have put in the minimum amount of hot solvent. You took the insoluble contaminants out by hot gravity filtration, and you got the solution through hot. And in this solution, let's say it's got your desired molecules dissolved in solution, and there's some kind of contaminant in here. And this is a different contaminant than the one we took out by gravity filtration. The idea here is that as this cools down, these desired molecules will no longer be solvated as well in the solution, because the solvent that was chosen isn't really the right match for that compound at room temperature. So what will happen is when the solution gets to a certain temperature, the desired molecules will no longer be solvated well enough, they won't have enough energy to stay in solution, and the desired molecules will start aggregating together. And if this process occurs slowly enough, the crystals will form with very, very slow equilibrium, and the desired, if a contaminant gets trapped in the desired molecule, it'll spit out the contaminant and take a desired molecule in, simply because the desired molecule fits better into the crystal. And you'll form these beautiful D crystals, hopefully leaving these C contaminants in solution. So over time, what should happen is that you'll see in your flask, on the bottom, crystalline material, which is the desired compound, but realize there's still desired compound in the solution, and hopefully there's still contaminant in the solution, okay? I want you to be aware that the desired compound will have some finite solubility in that solvent at room temperature. If it's soluble when it's hot, it's going to still have some solubility when it's cold, and you're only getting the excess out. It's kind of like solubility product in general chemistry. You're just getting the excessive D molecules. You're exceeding the solubility limit of the cool solution. And there will be plenty of D molecules left behind. You lose a lot on a recrystallization. But what you're hoping is there's so little contaminant, or the contaminant is just so much more soluble in that solvent that it'll stay in solution, okay? So you'll get this material out. Realize you could, in principle, isolate more of the D compound from the filtrate if you concentrated the solution. So there's such a thing as a second crop and a third crop and a fourth crop of material that could come out if you kind of start losing the solvent, if the solvent's evaporating off. But those crops will be increasingly crude, because if you get the solution concentrated enough to get the D that's still in solution out, you're more likely to also exceed the solubility of the contaminant molecules. I don't know if that makes any sense, but I want you to think about that a little bit. So there's such a thing as other crops here, okay? What would you want to do with the desired compound? You might think about this a little bit. You need to rinse the crystals, because the crystals will be coated in this mother liquor, and the mother liquor has the desired compound and the contaminant in it. And it's kind of coating the crystals. So you would want to rinse it with the cool version of your solvent, okay? So I hope that makes a little bit of sense. Now, once you get this material, you could run spectra of it, you could melt it. These compounds we're going to do melting points of. Remember, if a compound is contaminated, and someday I'll get into this theory a little bit, but if a organic compound is contaminated with another organic compound, the melting point tends to be depressed and broadened, okay? If the compound is pure, you tend to get a nice sharp melting point, and that's a colligative property you learned about in general chemistry called melting point depression, okay? So we can tell things are pure by how sharp the melting points are. That's very helpful. So lastly, the thing I want to say is just the fact that sometimes you can't find a single solvent that'll do the job, okay? And these Diels Alder products, we actually don't have a single solvent that'll do the job, okay? So in other words, people have, you keep around 20, 30 different solvents, maybe 15 solvents. You might find that you can't find a single solvent that the compound is soluble in it when it's hot, insoluble cold, and you're able to get rid of contaminants along the way. When that happens, what scientists will do is they will mix two solvents together, sometimes three, but usually two solvents, to get the kind of little bit of mismatch that they require to get the recrystallization to occur. And that's exactly the case with these Diels Alders. Now, when you come into the lab, there are several scenarios that could occur. The first scenario is, and I'm going to say this is your first scenario because I think this is where you're all going to be, or most of you are going to be. First scenario is your cap. I don't mean to make light of this, but a lot of the caps blew off. So your cap blew off, and your solution is just completely dry. It just looks like a big, massive crystal. So I think a lot of people are in that situation because the reaction sat for 2 weeks. That's why I was trying to cool them down last week. But you know, the reaction got kind of hot. And when they get hot, the lid can blow off. It even can blow that parafilm off. And then what happens is the reaction was taking place in dichloromethane. But if the dichloromethane evaporates, everything will kind of crystallize out. So reaction is completely dry. I think a lot of people are in this situation. We can deal with this. This is not a big deal. Okay, that's one scenario. I think another scenario is you grew some kind of magnificent gem-like crystals. Okay, it's going to be rare, but it could be that you'll have no crystals. These are the ones we're going to have to kind of fuss around with a little bit, Okay. What else could happen? The kind of the best scenario is you have needle-like crystals and some mother liquor. Okay, so let's talk about these situations because they really demonstrate what crystallization is about. All right, the reactions involved, for example, just as an example, one example of the Diels Alder, which I went over, is you're basically making this. And I went over this theory. What some groups are making compounds that look basically like this. Diels Alders make 6-membered rings, and I don't know how much of this we can do in class this week, unfortunately, because of the hurricane. Please watch that video. Some of you have studied this in class a little bit. And these reactions have very specific stereochemistry. So this is the product you would get from reacting 1,3-cyclohexadiene with maleic anhydride. Now, the reaction took place in dichloromethane. Okay, this is a solid, this is a liquid, and this is a solid. And there's the potential of other isomers that are also solids. So the idea was you do the reaction, it's sitting in dichloromethane. These get consumed over time, and eventually these crystals grow very slowly out of the solution, and then you isolate those crystals, and then you recrystallize them and make them really pure. Okay? So some of these reactions got completely dry. What that means is this is gone, this component is gone, the diene's gone. There's probably some maleic anhydride in here, and then this and some of its stereoisomer products, possibly. Okay? So the dry ones, they probably have maleic anhydride in them. Grew magnificent gem-like crystals. Well, if this happened to you, you should be really rejoicing. Get your cell phone out, take pictures of it, share it with your friends. These are really amazing to look at. What you're seeing there is what happens when crystal growth is very, 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 very slow. And when crystals grow very slowly, sometimes they'll form sort of a macroscopic structure that has a certain geometry to it. And I think it's a wonderful example of molecular communication. In other words, that individual molecules could aggregate in such a way that it's so ordered that you actually get a geometric shape that you recognize on a macroscopic level. You know, like they can form sort of like prismatic shapes and things like that, which shows the molecules, the geometry of the molecules can kind of be transmitted into a gross structure, macroscopic structure, which I think is amazing. And again, that's showing the molecules communicate with each other. The bad thing about these crystals is they tend to have liquid centers. And the center tends to be the mother liquor, and the mother liquor has the contaminant in it. So as soon as you show it to all your friends and take all your pictures, you're going to have to crush those crystals and get that liquid out. So the people who have no crystals, we're going to have to try to induce crystallization, and we'll talk about how to do that in lab. It's better demonstrated in lab. Needle-like crystals with mother liquor is the ideal situation. So I would say, so what we'll have to do here is induce crystallization, which we will do. I suspect by the time you guys get in there, you'll have crystals. So then these folks will probably have some kind of crystal and mother liquor. So I'm not going to lead you through the whole process. It's described in your lab book, okay? But, okay, most people, I would say everybody who has crystals of any kind, you're going to have to do a vacuum filtration. Okay, to get the crystals out, even the dry crystals, put them into a vacuum apparatus and then rinse with, it's going to be hexanes. Now, I want you to note that these compounds are very insoluble in hexanes. So all this is going to do is rinse the mother liquor off, or if you have the dry crystals, it'll just clean them off a little bit. Okay? All right, then, what do you want to do? You want to take the residue. Now again, the residue is what is left. And by the way, you are using small glassware here. Everything's small. You're not using big glassware. You're not using beakers. Like, don't use beakers. I say this all the time, and I fight this battle like all year. But you should be using your smallest Erlenmeyer flasks and probably your smallest vacuum apparatus. Okay? Tops your medium vacuum apparatus. Nothing big. Okay? So you have this little bit of residue. It might be like a half a gram or a quarter of a gram. This little bit of residue is your desired compound, but it's contaminated. Okay, so what do you have to do? Because we don't have a single solvent, oh, and the filtrate here, the filtrate is just sort of like the mother liquor of the reaction. And we might want that. Don't throw that out. Like, hold on to that, because if for some reason you have a terrible yield, we might have to fish some crystals out of that mother liquor, so don't throw that away. And don't start vacuum filtering until you've checked in with us. The residue, the problem with this compound, this is our crude solid. The problem with this crude solid is that it's there's not like one solvent that you could commonly use that would work for this. So in other words, I can't find like one solvent that's like commonly available in the lab where this residue would dissolve when it's hot and come right out while it's cold. So we're going to use a system of two solvents. Now the way you do this, it's kind of interesting, is you take the compound and you put it in a solvent that it's really soluble in, okay? And you do that when it's hot. So you put it in the minimum amount of a solvent it's really soluble in, okay? So it's kind of a weird thing. So what we're going to do is we're going to dissolve it in the minimum hot ethyl acetate. Now I'm warning you because this could be, for you guys, this could be like 1 milliliter or 2 milliliters, 3 milliliters of ethyl acetate. Okay, minimum amount. All right, now again, the compound's too soluble in this. And when something's too soluble in a solvent, if I cooled it down, I wouldn't get much out. It's solvated too well. And if you look at the structure of ethyl acetate, you'll discover it has some structural similarities to the kinds of compounds we're making. So I dissolve it minimum hot ethyl acetate. This could just be a few mils. Make sure there's a boiling stone. Use your hot plate. Okay, ethyl acetate boils about 77 degrees, which means you're not going to have the hot plate up too high. Okay, then what you do is you're going to add. Now, what if there was some insoluble contaminants? You would discover it at this point, and this is where you do the hot gravity filtration. But let's suppose it all goes into solution, okay? If you get it all in solution, the next thing you want to do is add, kind of drop-wise, an equal amount in volume of hexanes. Okay, now think about what this is going to do. Hexanes are just a mixture of 6-carbon alkanes. These are very nonpolar, this is very polar. So the idea here is we're going to take this compound that has a little bit of a dipole moment, a decent dipole moment, get it completely dissolved in hot ethyl acetate. If it has any little contaminants in them, we'll filter them out. Then what we're going to do is we're going to assume it wouldn't come out of the ethyl acetate because the ethyl acetate is too like it. It solvates it too well. So what we're going to do is start introducing hexane molecules into that solution. What's going to happen to the solution? And by the way, these are mutually soluble. So if I mix these together, they form a clear solution. So what's going to happen to our Diels Alder product molecules, which are anhydrides? They're going to be pretty happy in the ethyl acetate. Then you're dripping in hexanes. What's happening to the medium? The medium is becoming less and less polar. It's becoming more nonpolar. So the ethyl acetate molecules, all of a sudden, they're not surrounded so much anymore by ethyl acetate. Now there are hexane molecules in their environment. The environment is becoming less and less polar. It's becoming more and more nonpolar. It's becoming hostile to those Diels Alder products. Remember, Diels Alder products have a dipole moment. They look kind of like this. The ones we're making are anhydrides. They have this kind of structure. They have a dipole moment. So this thing, when it starts getting surrounded by hexanes, it's like, hey, get me out of here. This is not a good environment. So what happens? The Diels Alder adducts or products start sticking to each other because they'd rather stick together than be in this hostile hexane environment. And then what happens? You get that critical mass and they start crystallizing out. So what we're doing here is we're creating that kind of mismatched solvent system by putting two solvent systems together, one in which the compound is too soluble, one it's not soluble enough. In other words, it would take a ton of hexane to get this compound in solution if it would go in at all. Okay, so then what do? Well, your crystals will grow, and then when you get your crystals to grow, you're going to vacuum filter them out again, and this time you should be using your micro apparatus. Okay, lots of vacuum filtrations here. You'll have a residue. Okay, you'll have, I should be consistent. I don't know what side my residues have been on, but I'll put it over here. I think I've been a little inconsistent with that, but you'll have a residue. That's the desired compound, recrystallized. And you know, there's a mother liquor, and it's possible you could isolate more compound from that mother liquor, but remember, the contaminant is hopefully staying in solution. And these are other isomers and maleic anhydride. They're staying in solution. And if you start concentrating that down to get more of those desired molecules out, it's more likely you're going to have contaminant come out as well. I hope that makes sense, because solubility is related to concentration as well as temperature in the nature of the molecules. Okay? So then the filtrate, okay, I'm talking about the mother liquor over here. The filtrate is the mother liquor. And like I said, you could get more out of this if you want. Okay? Now the question is, what would you rinse this residue with? If you were using a single solvent, you would use the cold version of that solvent, and just a little tiny bit of it, because you don't want to rinse your crystals away. If you're working with a system of two solvents, you rinse it with the solvent it is less soluble in. So in this case, you'd want to rinse it with hexanes. Okay? So that's what we're going to do. All right? And then this crystal will take melting points. So hopefully through this experience, you will start to learn how to do recrystallizations. Thanks.